Good morning. I hope today finds you in good spirits. And what we're going to do today is we're going to work at solving some problems dealing with force. And we've given you some overviews, kind of some qualitative ideas about force in terms of larger understanding, but today we're going to get a little bit more into the nitty-gritty. And the thing with force is that there's so many iterations of these problems is that I can't possibly cover every possible situation. But what you've got to do is take the basic idea and be able to apply it across different situations. And that's going to require some plasticity on your part, some creativity in being able to see what the problem is asking. But you'll get more comfortable with it as time goes along. So the basic idea is this, okay? Whenever you face one of these problems, the basic premise that you should be setting up with is the object accelerating? If the object is accelerating, then Newton's second law of motion will be applied. Okay, and Newton's second law of motion should be one of your new toolbox equations, and that is F equals ma. And when I say F, that is a net force. Sometimes they'll put a sigma sign here, which means basically the sum of the forces, or sometimes they'll put a little subscript here saying net force. But my net force is going to equal mass times acceleration. Use this equation if the object is accelerating, and accelerating is speeding up, slowing down, and we're also going to find that it also incorporates changing direction, okay, when we talk about centripetal acceleration. But what if the object is moving or is at rest or at constant velocity? Well, if that's the case, then Newton's first law applies, and what you've got to do is make sure that when you add up everything, that the sum of forces equals 0. Again, if I've got a book lying on a table, that means that the force of the table on the book must equal the force of the book on the table. Otherwise, that book would shoot up into the sky or shoot down into the ground. If an object is at constant velocity, such as a car going down the highway on cruise control in a straight path, okay, then also the sum of force must equal 0. Gravity must be offset by the force of the road on the car, and the thrust of the car must be offset by the drag on the car. So the sum of forces is 0. That is kind of one of the hardest things with Newton's first law, is to realize that an object can be in motion and the net force is 0. If the net force wasn't 0, then the object would be accelerating, and Newton's second law would apply. So I'm going to do two demonstration problems here that are by no means the hardest ones I'm going to ask of you, but they're going to at least form a little bit of a basis for how you're going to approach this. So let's say you've got a 970 kilogram car starting from rest on a horizontal road, and it accelerates eastward for 5 seconds until it reaches a speed of 25.0 meters per second. What is the average force exerted on the car during this time? And before you even ask that, which law is being applied? Well, since Newton's second law deals with acceleration, and we know that that's going to be the equation that we use. So let's depict this situation. We've got a 970 kilogram car. In 5 seconds, its final velocity is 25 meters per second. Okay, it takes 5 seconds to do that. So the very first thing we need to understand is if we're looking for my net force here, my net force equals mass times acceleration. Well, thankfully, we already have our mass, but we need to determine our acceleration. And that's going to be the deal with some of these guys, is that you have to incorporate some previous ideas dealing with velocity into these problems. So if F equals ma, my acceleration is simply my change in velocity divided by my time in this problem. You'll have different variations of this. So 25 meters per second divided by 5 seconds, that yields an acceleration of 5 meters per second squared. So now it's just plug and chug. Here's my acceleration. Here's my mass. The net force on this car is going to end up being 4,850 newtons, with apologies to Mr. Chalmers in terms of significant figures. Okay, that is your answer. Box it up, ship it out. Let's try a different situation. Now let's say that we have a cat burglar weighing 600 newtons is suspended from cables, as you're going to see here. What is the tension in each cable? And before you ask that, what law is being applied here. So here is the drawing that they give us. We've got a cable attached horizontally here, and then a cable attached at a 37-degree angle right here. And we've got a cat burglar that has a weight of, it should be off that, a weight of 600 newtons. How can I make sure that the forces here add up to 0? Well, I know that whatever the weight is of this burglar going down has to somehow be offset by this weight pulling up by these cables. Now when I look at this drawing, I realize that this left cable here, let's call that T2, the tension in cable 2, can't offer any support there in terms of its vertical force. So all the force has to be applied by this cable, and you are going to resolve this force of this cable. Let's call this T1. Okay, this leg of this cable's force has to be what creates and offsets this 600 Newton force on this cat burglar here. So I know that my forces in my x direction are going to end up being 0, otherwise this cat would accelerate to the left or to the right, and I know that the forces in the y must equal 0, otherwise it would accelerate downward or accelerate upward. Okay, that's a nice thing about Newton's first law of motion, is that you can pretty much determine the situation. So in order to offset this 600 newtons, I know that the amount pulling down has to equal the amount pulling up. So 600 newtons of force pulling down has to equal whatever the tension in this first cable is times the sine of 37. Okay, because that's the component of this tension that is pulling up. So I can say that T1 sine of 37 equals 600 newtons. So then I end up saying T1 equals 600 newtons divided by the sine of 37. And so the tension in this first cable has to equal 997 newtons here. So I'll write that in. So that's all fine and well. But I know that my forces in the x direction almost equal 0. Also equal 0, I should say. So that means that the force exerted this way and the force exerted this way must be equal. So if that's the case, my tension in the second cable has to equal T1, which is this answer, times the cosine of 37 degrees, because that is now the adjacent leg of this triangle, and that's going to be the component of this resultant that is going to be pulling to the right. So now I go T1 cosine of 37, 997 times the cosine of 37. I'm plugging in this value for my T1. And so that ends up being 796 newtons. So I know that this T2 equals 796 newtons because the x component of this cable is also going to be 796 newtons. They're going to be equal and offset each other. So just kind of some follow-up questions here. What would happen to this situation if the horizontal cable were moved higher? Let's say I rearrange this and now set this cable so that's hooked up this way. What would happen to this format? What would happen to the system? Well, two things. One is now this is also contributing a positive y component to the efforts, to the force. And so what that's going to cause is a decrease in the tension in this cable because it does not need to provide that whole 600 newtons of force, and it's going to cause an increase in the tension over here. So there's kind of some repercussions of that. So I feel bad because I could solve these problems all day long for you, but it's probably better to throw you into the mix and have you try to tackle them and see where you run your ship aground. If you have not already done so, read these pages. They will help you. You can see some demonstration problems, okay, but only if you haven't done so. And then these are some problems here that are going to be involved. Some of they're probably a little bit more involved than what I showed you a little bit, but I think you can probably tackle them. You may have to incorporate earlier velocity equations that are in your toolbox for some of these. Check Slater to make sure you're getting the right answers. And if you have issues with these, make sure you do not hesitate to ask me send me a photo and tell me what your problem is, and I'll be more than happy to help you out with that. Other than that, we will see you tomorrow. We'll do some simulations related to force, and hope you have a great day.